probably heard about the word calculus or know a few people who take the class. But what is calculus? Calculus is the mathematics of change. It helps us understand things that are constantly moving or changing. But why do we need that? Imagine you're driving a car and your speed keeps changing, like slowing down at a stoplight or speeding up on a highway. Algebra can tell you the average speed, but what if a cop wants to know the exact speed of your car at the exact second when you're speeding? That's what calculus does. It zooms in and measures how things change instantly, which is called derivative. On the other side, what if you want to know the total distance traveled while your speed is changing every second? Calculus can add up all those tiny changes to find the total, which can cause an integral. These two ideas, derivatives and integrals, are why calculus is everywhere. In physics, engineering, medicine, and even AI. The big question, how did calculus begin? Let's travel back to ancient Greeks who made key contributions. One of the most influential Greek mathematicians was Archimedes. Archimedes is credited with developing the method of exhaustion, which was a precursor to integration. He used this method to find areas, volumes, and even the value of pi by slicing shapes into smaller and smaller pieces and adding them up. In a way, he was trying to do what calculus does, deal with infinitely small parts but without the formal rules we have today. Archimedes was so ahead of his time that some of his ideas are still considered brilliant. Alongside his time was another mathematician, Euclid, often called the father of geometry. Euclid lived around 300 BC and wrote a book called Elements, which organized and explained the principles of geometry in a logical way. His ideas about points, lines, and shapes gave us the basic language of geometry. But why does this matter for calculus? Because calculus relies on these geometric concepts, curves, areas, and tangents to describe how things change. Without Euclid's groundwork, the later discoveries in calculus would have been much harder to achieve. Now let's go into the medieval period, a time of transition for mathematics. Mathematical knowledge was transferred from Greece to Europe into the Islamic world. Greek mathematical texts were translated into Arabic and studied by mathematicians. For example, Ibn al-Haytham, a brilliant mathematician, also known as Ulzan, was famous for his work in optics and also explored geometry and algebra. He also calculated the volume of a dome by stacking infinitely thin slices, just like integration. He even worked with the sums of powers, which is the backbone of integral calculus. In the 13th century, an Italian mathematician named Leonardo of Pisa, also known as Fibonacci, changed the way Europe did math. His book, Liber Abaci, introduced the Hindu-Arabic system, numeral system, the digits 0 to 9, and the place value. This might sound simple, but it was revolutionary. Before that, calculations relied on Roman numerals, which made advanced math almost impossible. Fibonacci also studied sequences and sums, including his famous rabbit problem, which gave us the Fibonacci sequence. Now fast forwarding into the 17th century during the scientific revolution, Cavalieri, who was a mathematician, discovered the method of indivisibles, which was an early step towards calculus. The method stated that if two solids of equal height sit on the same plane with equal cross-sectional areas, their volumes are equal. Other mathematicians like Isaac Barrow, René Descartes, Pierre de Fermat, Blaise Pascal, and John Wallis began to discuss the ideas of the derivative. In the mid-1600s, Isaac Newton, who discovered gravity, realized that geometry could not explain motion, gravity, and planetary paths. He needed a new mathematical system that could describe change. Newton developed infinitesimal calculus, building on the work of earlier mathematicians. He faced a puzzle. How do you find the slope of a curve that is constantly changing? His solution was simple. As you zoom in closer, the second line becomes a tangent. That tangent gives you the exact slope at that point, which is the instantaneous rate of change. Newton called this process fluxion, and the changing quantities fluence. Today we know it as differentiation. Newton then realized the reverse of finding slopes is finding areas. Integration calculus calculates the space under a curve by slicing it into infinitely thin rectangles and summing them up. These two processes, differentiation and integration, are connected by the fundamental theorem of calculus. In 1687, Newton published his masterpiece, Principia Mathematica, using calculus to explain motion and gravity. His work dominated science for more than 300 years. Meanwhile, in Germany, another genius was on the same path. Gottfried Wilhelm Leibniz began exploring calculus in 1674, approaching it from a philosophical angle. He saw integration as adding up infinitely small slices, what he called infinitesimals. He also introduced the elegant symbols that we still use today. But who discovered calculus first? A fierce debate erupted, dividing Europe. Newton was credited the first to invent, while Leibniz received recognition for first publishing and for his notation. Leibniz described change as infinitely small differences, leading to the concept of limits, which introduced modern calculus. After Newton and Leibniz introduced calculus, the story didn't stop there. Two brothers from Switzerland, Jacob and Johann Bernoulli, took this new mathematical tool and put it to work. They weren't just solving abstract equations, but also figuring out how to apply calculus to real-life problems, like the shape of a hanging chain, the path of a light beam, and even the most efficient way to design structures. Their work in calculus would be essential for physics and engineering. It also contributed to the probability theory, which connects deeply with calculus like continuous distributions. Then came the greatest mathematician, Leonhard Euler, which formalized much of the notation we use today, including f of x for functions. He developed countless applications of calculus like differential equations, modeling motion, and fluid dynamics. But Euler didn't stop there. He gave the world the most beautiful equation in mathematics. The equation connected the five most fundamental numbers, e, I, pi, 1, and 0, in a single identity. To this day, mathematicians call it the most beautiful discovered. As the 18th century rolled into the 19th, calculus needed to grow up. First, it was based on intuitive ideas like infinitely small quantities. This worked but wasn't rigorous. Mathematicians like Augustin Louis Cauchy and Carl Weierstrass stepped in. They introduced formal definitions for limits, continuity, and convergence. These ideas made calculus rock solid, creating the rigorous framework that students still use today. The new position powered some of the greatest scientific advances in history. James Clerk Maxwell used calculus to create his famous equation that unified electricity and magnetism, which introduced modern electrical engineering. Without calculus, there would be no electric motors, no generators, and no communication technology. Moving into the 20th century, calculus became even more powerful. It was the mathematical engine behind Albert Einstein's theory of relativity, which transformed our understanding of both space and time. It also drove the development of quantum mechanics, which explains the behavior of particles at the smallest scales. These breakthroughs relied on differential equations, integrals, and the concepts of limits. And today, calculus is everywhere. It runs in the background of almost every technology we use. It helps engineers design bridges and skyscrapers that can withstand enormous forces. It models climate change to predict future environmental trends. In medicine, calculus powers imaging techniques like CT scans and MRIs by reconstructing 3D images from slices. Even the apps on your phone rely on calculus. When you scroll through social media or watch a video, complex algorithms optimize the speed and quality using calculus to minimize errors. In AI and machine learning, calculus is the foundation of how computers learn. So, from the ancient Greeks, Neon and Lebanese, and engineers today, calculus has been the force behind progress for over 3 centuries. It is the language of change. And without it, the world we know today wouldn't be here.